Hello, everyone. Thank you for joining us. On behalf of the Environmental Finance Center Network, I'd like to welcome you to today's webinar, Understanding Asset Criticality, Reduce Risk, and Optimize Operations. My name is Tess Clark. I work here at the Syracuse University Environmental Finance Center. I know many of you are interested in receiving certificates of attendance for this webinar. For this webinar in particular, the certificates will be provided by the American Waterworks Association. For attendees that have an AWWA customer record, your certificate will be uploaded within 30 days. For attendees who do not have an AWWA customer record, you will receive an email from AWWA requesting that you create a customer record by a specific date to receive your certificate. If you don't create this record, you will not receive a certificate. In order to get credit, such as a CEU, for attending this webinar, you need to check with your licensing agency. It's your responsibility to make sure this webinar meets your agency's rules and criteria for getting credit. This session is one of several webinars conducted by the Environmental Finance Center Network for our Smart Management for Small Water Systems project. The EFCM provides training and technical assistance to small public water systems, and we do this in all 50 states and 5 territories to help local systems achieve and maintain compliance with the Safe Drinking Water Act. Here you can take a look at our small systems team. Our network extends across the U.S. and we do have some centers in most major U.S. regions, as you can see here. And here you can see our areas of expertise that we focus on. We do workshops, trainings, and direct assistance, and we provide that on the variety of topics you can see here. So asset management, rate setting, resiliency planning, and more. We also have a small systems blog. You can learn more about water finance and management here. The blog posts feature lessons learned from our trainings and technical assistance, descriptions of tools, and small system success stories. You will also have the opportunities to subscribe to the blog at the end of the webinar. And one last resource I want to point out to you before we get started is our online funding sources map. This tool can help you get to the major sources of funding for your area, and you can access specific tables for that. So on the EFCN homepage, you go to the Resources tab and then click on the Funding Sources by State. That takes you to a map of the country. If you click on the state that you're interested in, you will find a PDF table that lists all the relevant funding sources for drinking water infrastructure for that state. The table sort of looks like the image on the left side of the slide. For each funding program, it includes the name, a short description, and contact person for someone who works there. Okay, and before I get the ball rolling with our presentation, we do have some polling questions that we're going to do. We're just going to get started with a couple just about your system. So first, what kind of water or sewer system do you represent? So just select one of the following options here. We're going to give you maybe 10 more seconds to do this. Looks like we have maybe 70% voted so far. I'm going to close this poll in 3, 2, 1. Great. So it looks like the majority of folks are from local government or municipal systems of the attendees that are water systems. And we have a couple people who are also from other utilities. All right, secondly, we're going to just ask you quickly about the size of your system. So if you're a water system, how many people do you serve? So just select the option that makes the most sense for you. We're going to give you maybe 5 more seconds to answer this. Okay, and closing this poll in 3, 2, 1. Okay, and of the folks that are water systems, it looks like the majority here today are large water systems with 10,000 or more people served. Also can see a good representation from medium systems, today 15%. Okay, and regarding our webinar today, we just want to ask you quickly about criticality. So this question, tell us, if you can, if your utility has ranked your system assets by criticality. Just click yes, no, unsure. And if you're not a water system, you can let us know that as well. Okay, great. I'm closing this poll in 3, 2, 1. And then lastly, before I turn our presentation over to our presenter today, we have one more question. Okay, is your utility able to perform all recommended maintenance? So I know this question, you may have to think a little bit about it, but to the best of your ability, tell us if you can perform 90% of more of the recommended actions for maintenance, 50% or more of recommended actions, if you can perform about 30%, or if you can't perform that much, under 30%, do your best to sort of see where you stand there. I'm just going to give you a couple more seconds here to vote. And I'm going to be closing this poll in 3, 2, 1. Great. So as you can see, a lot of people are able to perform their recommended actions. That's great. Nick will be so happy to hear that, I'm sure. And at this time, I'm going to go ahead and turn this over to Nick. Nick Willis is Program Manager at Wichita State University Environmental Finance Center. And he's going to discuss criticality today. And at this time, Nick, I'm going to turn it over to you.
Okay, thank you. And thanks for answering those last two poll questions. They are helpful to kind of better gauge about who is listening in here. All right, so the subject today is criticality, which is part of asset management. So this type of a webinar or in-class session, it's always good to try and get a similar kind of foundation. So the next few slides we'll be talking about that. Asset management, as defined by the United States Environmental Protection Agency, is maintaining a desired level of service for what you want your assets to provide at the lowest life cycle cost. This lowest life cycle cost refers to the best appropriate cost for rehabilitating, repairing, or replacing an asset. There's all sorts of different types of industries that utilize asset management in some form or fashion. And this is kind of the framework which we'll be utilizing today. So, we have a level of service, we look at life cycle costing, and we look at various methods to minimize those life cycle costs, such as rehabilitation, repairing, or replacement of an asset. In the utility industry, we're very, very capital heavy. We have a lot of fixed assets out there spread throughout our communities, and therefore that tends to be a cost driver for us. To put a little more graphically, in this framework, we commonly talk about 5 core components of asset management, and they can kind of come in any, you can start at A, B, C, D, or E, or F. And so there's not a necessary order that you have to do assets first, service level second, et cetera, but for the sake of a presentation, we do have to talk about that. The 5 core components of asset management are assets. What do I have? Where is it? And what kind of condition is it in? And how much is it going to cost me to rehabilitate or replace it in the future? Then we look at service level. Service level is the minimum service level that your utility can provide is defined by your regulators. So your maximum contamination level, minimum water pressures, things like that, that are, depending on what state you're in within your operating permit or federal regulation. Other service levels might be, how quickly do we respond to a customer complaint? What kind of fire flows do we have? What kind of pressures do we have over minimum requirements? things like taste and odor, as far as water as well. Criticality, we'll be talking about. Life cycle is really looking at the assets from the inception, the cost to procure, install, engineer, and then the cost to operate. And sometimes operational costs are the bulk of cost. For example, a high-use electric motor, 90% so of the cost may actually be the electricity used, while 10% is, purchasing that motor, purchasing and installing it. So life cycle costing can, understanding that and implementing that in asset management can really reduce some of those costs to running your utility. Funding, obviously you can have a good plan, a good asset management plan, but in order to operate a utility over the long term, you have to have some sort of an idea as to, where is the money going to come from, and to another degree, when is that going to come, and in what form it will be entering into our utility. All of these components are important to have in asset management planning. And just to note, asset management planning is very strongly encouraged by regulators, and in some jurisdictions, it's actually becoming more or less a requirement to operate a water utility. A little bit more in depth on criticality. Criticality in this framework fundamentally is assessing risk, and we're looking at two factors of risk, that being probability of failure and consequence of failure. So to put numbers on criticality, we would multiply probability times consequence. I'll show you kind of how that can lay out in the coming slides. And I noticed on the registration list, there are people from municipalities, counties, private water systems, and businesses. So when we are looking in this framework, we are focusing on risk to level of service, and compliance is the main framework which we view. We also look at risk of high cost to society and the utility. Other industries also make strong focus on business continuity risk, which is important in utilities, but a little less so in general compared to something, say, a petrochemical refinery or something like that. So if this is interesting to you, there's a lot of literature out there online that's freely available to learn more about things that can be buried within criticality and asset management. Before continuing, I'd also like to say a few words about risk. Risk is ever present in life. Anytime you walk downstairs, take a shower, drive a car, there is a risk of harm being done. Running utilities is no different. There is a risk your utilities will fail at some point. Even if you want to minimize risk to the highest degree possible, we're going to put in everything new in our utility. Even that new infrastructure is a balance of risk of failure versus cost and other constraints. A new pipe can break. A new treatment plant can produce non-compliant water. And given the economy of your system, the nature of the geography, the economic condition, all sorts of things go into a balance of risk versus other constraints you may face. You cannot eliminate risk, but by going through asset management planning and looking at criticality of components, you can both reduce risk through changes in, through optimizing maintenance, changes in how things are done in your utility system, and also just as equally important, you can also plan for that risk. What will we do if this asset fails? If you have a plan in place, you save a lot of time from figuring out what to do in the moment by having a plan already completed. When we look at that probability of failure versus the consequence of failure, you can multiply them in some form or fashion. A high probability of failure is on the horizontal axis on this slide. You can see it goes from very low probabilities to high probabilities. Likewise, the vertical axis is the consequence of failure. You can go from a very low consequence of failure with an asset to a very high consequence of failure. Consequence being both to your utility's level of service, direct cost of asset failure to your utility, and also outside entities which may bear cost from utility failure. For example, restaurants will typically close down if you're under a boil water order. That's a consequence of failure of treatment or loss of pressure in your system that you don't bear directly, but is nonetheless there. So when we look at ranking our assets by criticality, we look at the probability of failure, and you can plot that on the horizontal axis, and then you look at the consequence of failure, and you plot that on the vertical axis where those two cross. Then you could kind of quadrant off things here and say that, well, this is a high-risk asset, this is a low-risk asset, or a medium-risk asset within my utility system. And after you've kind of gone through this process with some of your assets, you can begin to say, okay, maybe this is an asset I need to pay a little more attention to, maybe maintain a little more frequently. And likewise, those that are low risk, maybe we can minimize the amount of attention we spend on them. Another important thing to look at when we look at probability of failure is, how does an asset actually fail? So a lot of the assets you have within your utilities may have experienced failure in the past. That same type of failure is likely to occur in the future if you have, same make and model, same material, that sort of thing. So it's important to look at what has happened and then what can happen in the future. Another way to gauge types of failure that may occur in the future is to look at things such as the American Water Works Association, where they have other utilities have a longer time frame experience with the same sort of assets that you have in your utility. And that can be a good source. So things like conferences, trade magazines can be pretty valuable at looking at how can your assets fail in the future. And then what can reduce the probability of failures? And we'll be talking about some of those going forward. So looking at the probability of failure, it's very important that you and also the decision makers of your utility, that failure does not necessarily mean broken. We tend to think of failure in utility industry as something like a water main that is burst. Or a fire hydrant that no longer works. And those truly are failures that are broken. What we would maybe have you entertain is to answer the question, how can this asset fail to deliver what is intended to deliver? And so failure can come in forms that aren't, broken parts everywhere. They can include things such as environmental changes, regulatory changes, capacity loss or degradation, power loss for those assets that require electrical power. Water quality or quantity declines can also occur, and also to some degree the interaction with your community can make some components of your utility obsolete going forward. So that interaction with community can also play a role in some utilities. When we look at environmental changes that can cause failure, this has been a fairly common occurrence in many small water supplies throughout the country. What happens here is that a previously compliant water source becomes polluted over time. What has been driving a lot of this is nitrate pollution. So you might have some groundwater wells in your utility. Over time, nitrates have increased, and they eventually get over the legally allowed limit. Likewise, we are seeing blue-green algae events seem to crop up more and more in more water supplies, more surface impoundments. These are environmental changes. So all of your assets are fine, but your source of supply is, due to environmental changes, is going to cause failure to meet that level of service that you're supposed to deliver to your customers, through things like the maximum contaminant level for nitrates. We also have regulatory changes. There's probably many people on the line who have had this happen to their system. The example I'm going to go here, the maximum contaminant level today is 50, and there's been, public health studies, epidemiology, things like that, and it's determined that in the future we're going to limit this pollutant more. The maximum contaminant level drops to 5 as of 2025. So your treated water may be 25, meaning you're compliant today, but come 2025, assuming nothing changes, you will be non-compliant. There's very little you can actually do with regard to that, but you still have to keep that in mind as a way your utility can fail, again, on the source of supply, because of regulatory changes. So one thing that utilities that are putting in new treatment are often looking at what type of infrastructure can I put in, what kind of treatment technologies can I put in that will serve as a more or less an insurance policy to be able to treat some of these potentially new lower limits sometime in the future. This can be a pretty tough one because it's so far out of your control, but it is something to consider when you're looking at criticality of your assets. Is this something that can fail to deliver the minimum level of service required by regulators because the regulators have actually changed what is required? You also have slow failure over time. As infrastructure ages, on the water utility side, we see things like pipe tuberculation. That is the picture shown here. Basically, the functional diameter of the pipe gets smaller and smaller over time. So the level of service might have been a 1,000 gallon per minute fire hydrant. Because of this tuberculation, the fire flow has dropped to 700 gallons a minute. That is a slow moving failure where you fail to meet the level of service required from the level of service desired for your utility assets. Another common thing is pump wear. So you might have pumps that still turn on, don't make any weird noises, but don't pump the same gallons per minute as they used to. That's a likely indicator of wear that has gone on. So the capacity drops over time. Well street and clogging is a similar phenomenon to the pipe tuberculation. There's less area for water to flow through. And then slow meters. How you get your revenue, you sell water. Slowly over time, many water meters will read a smaller and smaller percentage of the actual water flowing through them. This is, again, one of those capacity loss failures. The water still flows through the meter. You still get revenue from it. It's just not what it should be, not what was desired when those meters were installed. The issue of power loss is something that many utilities deal with on a somewhat frequent basis for some of their assets. Water and wastewater utilities often have assets scattered throughout town that may be prone to power loss. Fundamentally, electrical power does fail, and it probably will fail regardless of your location. There's a lot of options to deal with power loss, though. In many locations, the best course may actually be to do nothing. So this would be something, for example, if you have a water utility, you have wells scattered throughout town or outside of town, maybe you don't need to back them all up because they're already redundant. So maybe you just back up some of them and let the power fail to others. You'll have plenty of water all the time. A second power feed is often done, particularly on things such as treatment plants. So you have major power line coming from the west and coming from the north. That'll help supply some redundancy. And then we look at things like backup generation. This can go from mobile, such as in this picture. So you can tow this around and run assets when you need to run them to keep you in water, or to, as many people on this webinar are probably in charge of both water and wastewater utilities. You can move this from, say, a well or a pump station and then move it over to a sewer lift station. That's kind of my experience in working with mobile generation. There's also permanent generation. This is more likely to be on those larger assets such as treatment facilities, major pump stations, major lift stations. And the other question to ask when we're looking at power loss is, do we try to run all of the equipment we have or just partial? Oftentimes, particularly large facilities are not fully backed up on backup power generation. So your plant running at full capacity may require 1.5 megawatts. You only have a 1 megawatt backup generator. Your operators need to understand what they can and cannot run when running on backup power, if that's the case. Another type of failure we can see on our assets is quality or quantity declines. There's many locations in this country that are seeing declining water tables in groundwater supplies. This is similar to things like a pump wear. Over time, you'll see decreased pumping rates, and in some locations, you may see water quality changes. I'm familiar with many locations that have, as you go deeper in the aquifer, you see increased salt content, for example. You can also see surface water changes. So this might not really be a regulatory issue, but it might be a customer service issue where taste and odor change over time. Likewise, you can see salt levels increase. Oftentimes in times of drought, the salinity of water supplies, the amount of salt in water will increase. And to most customers, that doesn't make much of a difference, but you do have to think about some of those very sensitive customers that have to have very specific water quality. So maybe on the industrial side or something like a dialysis facility. pH can sometimes change rapidly. Likewise, turbidity is probably the most common one. So, how clear is that water? You get a major rainstorm, your clear lake may look like mud, the next day because of high runoff and surface erosion. And then probably the most difficult type of failure that's not, completely straightforward to talk about is the interaction of your utility systems with your community. There are many utilities out there that are either over or undersized, or they can actually be both, depending on how your community is laid out with respect to your utility infrastructure. Those utilities that are seeing growing populations may be undersized for the actual demands that are being placed on them today. These are places you'll often see, having to have some type of water restriction to meet either instantaneous pumping or restrictions on water rights or total amount of water available. You also have a lot of utilities that are facing shrinking populations, and these are quite difficult to deal with because you have oftentimes significant financial implications from shrinking populations. But in a water utility with shrinking populations, you'll often run into issues with stagnant water. So a utility that was designed for 20,000 people and the town is now 14,000 people is going to be using significantly less water than was designed for. And that means you have, larger pipes, larger storage tanks, and this can lead to water quality issues and also compliance issues in some cases. Because of shrinking populations, towns that are shrinking in population tend to not have very good economic indicators either. Oftentimes household incomes are low, and you have issues with meeting financial goals and policies as a result of this interaction with your community. We also see economic and technological changes. So A utility that was designed to provide a lot of water for heavy industry may now provide a lot of water to, you know, downtown lofts or, you know, remodeled office towers, and the type of utility services that is needed may be quite a bit different. So the world changes around us all the time. But our utility systems have often been in the ground for 50 or 100 years. And we see both economic changes, you know, how people make their money in this country is a lot different than 50 years ago, and technological changes as well. One of the technological changes is that most uses are getting more efficient. So many of those utilities that are out there and are able to supply high amounts of water to specific customers, those specific customers are probably attempting to reduce their water usage, both from an economic and kind of a corporate social responsibility framework. Now we're going to move to redundancies. Redundancies help reduce the probability or consequence of failure, depending on how you want to look at it. So most or many parts of water and wastewater utilities are engineered, designed, and installed to have redundancy in them. For this presentation, we can look at the Oxford dictionaries and look at two different meanings of redundant, both of which are somewhat applicable to water utilities. The first of these is able to be omitted without loss of meaning or function, focusing on function here. And the second definition here is redundant of a component is not strictly necessary to functioning, but included in case of failure in another component. If we look at these air compressors on the right, these are probably 100% fully redundant. And in addition to having, you know, two air compressors there, they also have storage tanks that can probably take the load of the plant, compressed air needs, for, you know, some period of time while the compressor above them is out of service for repairs or maintenance. Then we have the four water towers. These are actually on an old Army ammunition plant in DeSoto, Kansas. I don't know if they're all in service anymore, but the design redundancy is somewhat unique. You don't see this type of layout very often. When we're looking at redundancies, again, redundancies, the redundant assets on the air compressors, having a redundant asset doesn't reduce the probability that the air compressor on the right is going to fail, but the consequence is greatly reduced. The consequence is that your plant is still able to keep running with the other air compressor, and most of the consequence now becomes a financial consequence only to your utility instead of, you know, loss of treatment capacity or other problems that may have occurred at the plant. One thing that utilities often have are also partial redundancies, and this can be difficult if you're stepping into a treatment plant that you maybe don't have the design specifications on or any of the original operating manuals. How do you tell if a plant is partially redundant or fully redundant? So oftentimes repetitive equipment is either fully or partially redundant. I have no idea if this top picture is fully redundant at all. Likewise, this bottom picture, as you add more and more pumps, you may not be able to tell just looking at it. You're going to have to do some research as to whether you are partial redundant or fully redundant. So when we look at this bottom photo, some of the questions we may ask are all the pumps the same capacity? Oftentimes, high service pumping stations are not. And then we have to look at what's required for peak flows. And that also gets into the issue of, you know, duplex pumping. One pump may put out 700 gallons a minute, but when you turn a second one on, it doesn't make it 1,400 gallons a minute. So knowing some of those hydraulic implications is important when looking at partial redundancies. So when we're looking at partial redundancies in the broader asset management framework, a couple things you can kind of keep in mind. Generally, if you determine that you have a partial redundancy, you're going to see your maximum capacity of your assets limited to some degree. So, for example, a pumping station that is partially redundant may drop from 1 million gallons per day if everything is in service to, say, 600,000 gallons per day when one of the pumps is out of service. How this impacts your utility operation is going to vary from utility to utility, but oftentimes you will be able to meet your average demands. So your average demands may fall below 600,000 gallons per day, but you may not be able to meet your peak demands. So your 1 million gallons per day, you're not going to be able to meet. So in order to deal with this risk, you can plan a response for a failure in peak demand. So, for example, if you have a lot of water used by your customers on their lawns, you would plan a communication program and maybe some ordinances or operational rules to limit irrigation should you lose some of that pumping capacity. Another thing to keep in mind with partial redundancies is that when you have a failure in a partially redundant system, you often have little to no redundancy after that first failure occurs. So once that first failure occurs, that kind of should put your feet to the fire and really get things up and running in full capacity in a short amount of time, because you have very little redundancy after that first failure will occur. And when we look at redundancy and you look at your system and say, well, we're only partially redundant in many of our pumping stations. The reason this has been done is likely goes back to economics. So in order to have a fully redundant system and minimize that risk to the full degree practicable, you might not have been economically in a place to be able to do that because of high utility rate burdens or some other factor that was playing into that. Another thing to look at when we look at redundancy is non-like-for-like redundancy. So all of the pictures I was showing you with the air compressors, with the pumps, those are like-for-like redundancy. Pump A fails, I turn on pump B. Compressor A fails, I turn on compressor B. Many utility systems have a lot of non-like-for-like redundancy, and these are important to identify in your utility because they allow you to operate at lower risk if they're being utilized. So some of these examples of a non-like-for-like redundancy may be an emergency supply interconnect with a neighboring system. So you have the valve shut, but in case of failure of your water supply, you're able to get water from your neighboring system. That is not like for like, but it still potentially meets the needs of your customers. Elevated storage tanks. These serve, depending on your utility system, to some degree to back up your pumping units that supply the pressure to your system. Going as simple to a customer meter. If a meter fully fails and is either no longer flowing water or is leaking significantly, you can always put a straight pipe in there. Your customer still is provided with water, although there's some financial implications on the utility side. Control systems, we haven't really covered those at all today, but some redundancy in your automatic control systems is that you can turn that switch to hand. So you can operate your utilities manually in case of failure of control systems. You may also have raw water supplies. So you have emergency water supply wells, a backup lake, whatever it may be. Your raw water supplies with varying quality may be a non-like-for-like redundancy. So these are also important to keep in mind when you are looking at your utility systems. So let's look at redundancy and graph out some of the implications of this. Again, we go back to this diagram. In the very upper right, we have a single pump. No redundancy at all. It's an old pump. So going to the left here, we rebuild it. We see the probability of failure reduces quite a bit because we have a bunch of new parts in there. It's been inspected and reinstalled. We can also put So that's one way to reduce probability. Reducing consequence, we can put elevated storage with that pump. Therefore, if the pump goes down, we have a few hours or a few days to make repairs before your utility is out of water. You can also put a redundant pump, for example, further reducing the consequences of failure. And maybe the lowest consequence of failure, and this will vary, again, depending on utility systems, this is just an example, might be having that single pump with an interconnection with a neighboring utility. When we're looking at using criticality to inform our maintenance, the general theory here is that the investment of your resources, spare parts, money, and the thought time of your utility managers and operators should be guided by the criticality of your utility assets. We don't want to spend a whole lot of time and money repairing that asset that has a low probability of failure and a very low consequence of failure. And to some degree, we might be rethinking how things have been done in the past. Again, we have the same probability of failure, consequence of failure graphic here. The numbers on this slide are just an example. Don't go and change your utilities operation based on this. It's just kind of a thought experiment. So if you have those very high-risk assets that have a high probability of failure and a high consequence of failure, then you would look to, devote most of your maintenance budget on those assets. The theory being that if we can minimize the failure of these, we minimize the risk of service loss to our customers. And then, the 30% of budget on those high consequence of failure, but relatively low probabilities. Only 5% of your maintenance budget being spent on those assets with low consequence of failure, low probability of failure. And then 20% on the higher probability of failure, but lower consequence of failure assets. Again, just an example, but this is a way to rethink about where we are spending our time and money in utility maintenance. We're going to put this in practice. I would venture to guess that many of you that operate water utilities have gate valves throughout your system. These serve to isolate parts of your utility system in case of main break or construction. Or maybe a customer needs to put a big tap in. Most recommendations are saying these should be exercised, fully turned shut, fully turned open, fully turned shut, fully turned open at least once a year. However, I would venture to guess that many of your utility systems are not doing that at that frequency. So if we have a certain amount of time and resources to devote to valve exercising, how do we do it that reduces the risk of running our utilities to the maximum degree we can? So what we look at here is to try to rate the valves on criticality. So if this valve were to fail, it would be a very high risk, high consequence, high probability of failure. We would try to exercise that one on the recommended schedule. But you may have a 4-inch valve on a dead-end cul-de-sac line that's relatively new. That's probably a relatively low consequence of failure on that valve, and probably a relatively low probability of failure on that small new valve. So we would devote our time and resources to exercising the critical valves first, and then maybe do a less frequent schedule on those non-critical valves. However, you're working in the real world, you're going to have to balance this with the known condition of the valves. Maybe outright replacement if you know you have some valves that are very high probability of failure. You don't necessarily have to maintain them all. You can actually replace some of those and change the criticality of them. Also, do you exercise valves if you know you're replacing the water line 2 or 3 years from now? So if there's a known end life on your asset, how do we maintain things? And then many times when you come up to a gate valve, there's 3 or 4 very nearby. while we're already there, should we exercise those nearby valves, even if they're less critical? So there's kind of a lot of questions and thought processes you need to go through on that. That being said, valves aren't your entire system. You can do this exercise for your gate valves in your water distribution system, but you have a lot more assets than just those valves. So when we look at the whole system as a whole, most water utilities struggle to have enough maintenance dollars and time to do the maintenance. So we have to look at the aggregate maintenance of your most critical assets, not just the most critical valve or pump, in order to minimize the risk of running your utility operations. So what you might want to consider are, and these are just examples of things to consider, where can my maintenance reduce the life cycle cost to my utility? Sometimes maintenance on very expensive pieces of equipment might be extending the life of that could really reduce life cycle cost, where maintenance on a very cheap piece of equipment is not really going to change the game when it comes to life cycle costing. So you might not put a whole lot of maintenance on that weed whacker, the handheld weed trimmer, to keep things looking nice at your water treatment plant, but you spend the maintenance time and dollar on some of the expensive equipment within the plant. Where can I detect future problems by having a person go out and maintain assets? There's a lot of value in being on-site, listening, and feeling assets. If they're making a weird noise, generating excess heat, if they're obviously vibrating, if they're out of balance. So where are future problems likely to be detected? Also, how can I improve emergency response in my utility operations? How can I increase the knowledge of the system for utility operators, particularly newer ones, so that they understand kind of how the system's laid out? And then how can I maintain the desired level of service? With this, I've thrown quite a bit of information at you, and we are now able to take questions. So I'll go ahead and Tess, if you want to take over from here.
Yeah, so go ahead and try to get your questions in, and while we are waiting, I'll just run through our last few poll questions. We're just going to circle back quickly to our question about our blog. So go ahead and answer this question, and at the same time, if you can, think of those questions and we'll queue them up for Nick. So just quickly, if you'd like to subscribe to our blog, now's your chance to do that. Going to give you a couple more seconds to put your vote in. Right, and I'm closing this. And then secondly, I'm just going to run a quick poll. This poll is about receiving in-depth technical assistance. If you're at a small system and you know you need some assistance, we can get in touch with you if you respond to this quick poll. Great. So most people have responded, so I'm going to go ahead and close this. Thank you for taking the time to do that. Awesome. Great. So we do have questions. The first one just pertains to the availability of the PowerPoint. Yes, it will be available and posted on efcnetwork.org. That's going to be in about 2 weeks. Any other questions, please go ahead and get those in. In the meantime, we also have a evaluation for this webinar that I'm going to push out through the chat box. And when you get that, feel free to fill that out for us. Great, so it looks like we do have a question. This question for you, Nick, this pertains to SCADA. How do you feel about reducing operational and maintenance costs by utilizing SCADA?
So yeah, this is SCADA stands for Supervisory Control and Data Administration. I don't know. It's an acronym that the system basically allows for remote sensors, allows for remote turn on and turn off of assets, monitoring of things like system pressure, tank level, chlorine levels. Yes. Reducing maintenance with SCADA may not be its biggest benefit, but certainly having a SCADA system in place can free up a lot of labor to be able to maintain assets that aren't being maintained. For example, the utility I used to work at, we had a well field 12 miles south of town. Before they put in their SCADA system, in order to turn on a well, somebody had to drive at least 24 miles round trip. And there were some dirt roads, and you had to open gates and things like that. It took 2 hours to turn a well on or off. With the SCADA system, it is now a few seconds of operator decision making, ensuring everything is functional, and then they can turn it on from the treatment facility. So there's a whole lot of value to SCADA systems, most of which is probably not on the maintenance side. That being said, there are SCADA systems in processing facilities such as food processing, refining, that do a lot of remote sensing that can, ding you when maintenance is needed. I hope that kind of answers the question.
Yeah, so we do have a couple more questions beyond that one, so I'll go ahead and try to get so we can move on. This question is about references. So the question is, are there good references to quantify the consequences of failure? Often evaluation of likelihood of failure or consequences of failure is in a point scale, but this can obscure prioritization. We prefer to get dollars as risk, but references are hard to find. Do you have any suggestions for that?
You can definitely get some of that information on the consequence of failure. So let's take, for example, a pump. Part of the consequence of failure is the cost of that pump. So that is reasonable estimates are obtainable from suppliers to get that side. The other consequences that are maybe environmental or social are going to be site specific, and I think you'd probably have to get some sort of a consultant on board to put a dollar amount on it, because a prolonged boil order in a community that has a whole lot of restaurants because they're on a major interstate highway, it's going to be a lot different cost in that community than to a community that doesn't have any restaurants at all. So I think the quantification on the outside consequence is very much going to be a pretty in-depth outside consulting type of a situation.
Sorry,
I don't answer.
No, I'm cutting a little bit there, cut in and out for a second, but we still have a couple more questions, so we'll try to get through them as quickly as possible. What do you think of using infrared cameras for temperatures is our next question.
Yes, that is something that has gotten super cheap in the last few years, and there's some decline in the quality, but the value of the information is there. Infrared can show you problems with your electrical system. It can show you places where equipment is having higher friction than it should be having. So you can use infrared. There's many kind of cameras that mount to your smartphone that make your smartphone an infrared camera, and these are sub $1,000. And I think that's, yeah, more systems should use that type of infrared if they have a lot of either electrical connections or moving parts that are visible and readily accessed.
Awesome. So I think we have time for maybe one more question, and so any questions we don't get to, and there are definitely a few, we will hang on to those questions and follow up with you after this webinar. So the last question for you, Nick, is, are there recommendations regarding testing or periodic use of interconnected adjacent utilities backup connections?
I have never seen one. I think at a minimum you would want to ensure that the valves open and close on an annual basis, and you probably should be able to have most interconnections allow for that without blending of water. Oftentimes interconnections may have somewhat non-compatible water, particularly those that are emergency interconnections. So, but certainly all of the assets that are within that interconnection should be maintained at otherwise recommended intervals. For example, if there's a hydrant there, you should exercise that hydrant, ensure that it works on whatever frequency it's recommended.
Yeah, so we definitely have a few more questions. I don't know that there's time to do an in-depth response for those. So I'm going to say, Nick, do you have any closing comments or anything to follow up on based on the last few questions?
Not really. I hope that in the short time we were together that you at least learned something about criticality that's a little more in depth from what you may have seen in kind of the introductory asset management classes. Yeah, if there's any question, feel free to give me a call or shoot me an email, and I can try and do a little research for you or help you out. Thank you.
Awesome. Thanks, everyone. Hopefully, we will get back to you with the rest of those responses shortly, and this webinar will be posted within the next 2 weeks on our website. Thanks, and talk to you soon.